Hi, I'm David, and I would like to present optimizing distributed protocols with query rewrites. In case you'd like to talk to us at the conference, I've highlighted everyone who will be here in person in red. You can also see them right here. Distributed protocols like 2PC and Paxos lie at the core of many systems and databases, but they fundamentally do not scale. So traditionally, to solve this problem, experts have analyzed these protocols and used clever insights to come up with entirely new protocols, and then proved that these new protocols satisfied existing specs. Unfortunately, because these protocols are complicated, their proofs are also complicated, and we often get this process wrong. So we present an orthogonal approach. Instead of creating entirely new protocols from scratch, we'll use small local rewrites to incrementally modify existing protocols until we have one whose performance rivals that of existing hand-optimized protocols. This might sound a little bit like a query optimizer, and that's where we were inspired by. So if you think about it, if you have a query like this filter over joins, you might throw it into a query optimizer, which might do small optimizations, like changing it into a left deep join or doing predicate pushdown, right? We just want a query optimizer that understands how to scale distributed protocols. And there's two main benefits to this. So first, notice that I've moved the check marks from the protocols to these rewrites, and that's because we're now burdened with proving that the rewrites are correct, not the protocols. So the first advantage is because these rewrites are small and local, our proofs are also small and local and much easier to get right. The second is because we've proven the correctness of these protocol agnostic rewrites, we can use the same rewrites to optimize any distributed protocol, including hand-optimized solutions. These are the two main points of this paper, so I'm just going to emphasize this again. We've shifted the proof burden from protocols to rewrites. And by doing so, because the rewrites are small and local, the proofs are also small and local and much easier to get right. The second is that these rewrites can now be applied to any distributed protocol. Okay, now let's take a look at how this query optimizer might apply the rewrites. We'll zoom into one of these steps, and we'll generalize Paxos into any protocol. If this protocol meets some preconditions, then we'll apply the rewrites and output a rewritten protocol. Implicitly, we'll assume that somebody has proven this right, and that's our goal for this paper. But the power of this approach is that because the output is still a protocol, we can feed it back in, right? And then we can apply another rewrite and another rewrite. We can stack these rewrites on top of each other. All right, now let's take a look at how we actually do these rewrites then. So first we'll cover the protocol, the rewrite, the precondition, and the proof. And you can follow along on the top right. Okay, the language. Because we want to optimize any distributed protocol, we need one language to describe all distributed protocols. So in the paper, we use a formalism called Daedalus, but here we'll just use data flow for simplicity. So this rectangle is a node. These dash arrows are message passing. This circle represents an operator. Here it's a filter. And this arrow represents data flow. So roughly what this node is doing is it receives chat messages, filters them, sends a message out telling you that the message has passed the filter, and then joins those filtered messages with a set of members and broadcasts the message to each member. So in other words, this is a chat server. All right, now that we have a protocol like this, how do we optimize it? Well, there's two fundamental scaling rewrites that we will consider. So the first is decoupling. This just means that we're moving logic from one original node to another node. And the second is partitioning. So this means we're splitting data across nodes that execute the same logic. All right, now let's try to decouple our chat server, right? If this chat server is the throughput bottleneck, maybe we'd like to decouple it. Right? We'll just move the join logic to another node, change the data flow into message passing. But the big question here is, do we know if this is correct, right? Hard to say. This is where preconditions come in. So technically here, we're allowed to decouple because node B is set monotonic. All right, I'm going to get a little specific here, but node B is set monotonic if, given a set of inputs I, which is a subset of the inputs I prime, the outputs of B applied to I must also be a subset of the outputs B applied to I prime. In other words, the more chat messages and the more members that node B receives, the more chat messages it will send to all those members, right? The cool corollary here is that this makes node B order insensitive. So if you think about it, if you first add a dog to the system and then a message hi and then add a cat, or if you add the dog, the cat, and then the message, it doesn't matter. Both the dog and the cat will eventually receive the hi message, right? The ordering didn't matter. Okay, so now let's try to use this precondition to prove correctness. But first we have to talk about what does correct even mean, right? We're not trying to prove that the rewritten protocol is correct. We're trying to prove that our rewrite is correct, that it doesn't change what the program was doing. So we will prove observable equivalence. This means that to any observer who can send or receive messages from this protocol, the possible executions it could have witnessed after the rewrites must be a subset of the executions it could have witnessed before the rewrites. In other words, any execution it witnesses in the rewritten protocol must have been possible in the original. So it still must be safe. All right, now let's try to prove that this monotonic decoupling we described is observably equivalent. This doesn't seem that hard, right? Because we didn't actually change that much. All we did was we swapped this data flow for message passing. But that's the problem, right? We broke atomicity. So if you think about it, when a message arrived in the original protocol, it must have been processed at one moment in time. This is no longer true. So when a message arrives at the new protocol, it's processed at the same moment in the first node, but at a different moment in time in the second because of this extra message passing we added. And that's a problem because now something might sneak in between, right? So I claim this is not a problem for a monotonic decoupling. You can't observe this. But let's take a look at an example where this might be observable, okay? So we're going to take our chat server example from earlier, and we'll modify it so it's non-monotonic. It's very simple to do that. All we have to do is we change this join so that it only, new messages only join with current members, okay? So whenever you add a new member to this chat server, they don't receive historic messages. They just see what's new, okay? Let's take a look at how this behaves. So I have a space-time diagram here on the right, the observer and the node. And let's say the observer first adds a dog to the system, and then it sends a message, good boy, right? The dog is a good boy. We want to tell him that. When this message arrives, it must have been processed by this node atomically. So it must have passed the filter and joined with the dog in a single moment in time. And that means that if the system tells us that the message passed the filter, then it must have also joined with the dog, right? So now if we add the cat after we know that the message passed the filter, because by passing the filter, it implies the message was atomically processed and joined with the dog, then we know that the cat won't join with this message, right? In other words, the cat won't receive good boy because the cat, as we all know, is not a good boy. Okay, so now if we send the cat, maybe at some point in the future, the dog will receive good boy, but the cat never will, right? Because the message was atomically processed and we know it has already finished processing, right? Because we received the ACK. Now let's look at what happens once we decouple this. Again, space-time diagram, except now we have node A and node B. So we send the dog, we send the message good boy, and the system tells us that it passed the filter. Okay, if we add the cat now, something bad might happen. Maybe only now does the message pass from node A to node B, right? So when node B receives this message, it joins with both the dog and the cat. And the dog and the cat both receive good boy, but that's bad. The cat is not a good boy. So what happened here, right? Well, if you look at it, we really stretched this yellow region, right? This yellow region used to be something that was atomic. Both the filter and the join would have happened at a single moment in time. But because we stretched this apart, now when the cat is added to the system, it could arrive in between this originally atomic operation. And that was just not possible, right? So if we go back to our original example, I assert that if node B was set monotonic, then because message order wouldn't matter, this is okay. Both the cat and the dog should eventually receive this message. I actually don't have more time to go into why monotonic decoupling is correct, so please read our technical report. Also, there are a ton of preconditions we don't have time for. Please read the technical report. Let's look at some numbers. Okay, so we implemented voting, 2PC, and Paxos in Daedalus, our formalism, which was compiled down to HydroFlow, which is our data flow runtime from our group Hydro. We ran them on GCP with VMs each accessing 4 CPUs, and we applied these rewrites manually. So we found the bottleneck of protocols, decoupled it, and then tried to find the next one. And for every node that was partitionable at the end, we would partition it 1, 3, or 5 ways. In case you're curious, here's all the rewrites and preconditions we used. And here's our results. So for voting, 2PC, and Paxos, the throughput was increased by 2 times, 5 times, and 3 times, respectively. And for Paxos specifically, this is comparable to numbers from hand-optimized Paxos running on the same hardware from prior work. I don't show latency here, but that was largely unchanged. You can check it out in the paper. What I think is really cool is that we did not have to understand these protocols, right? We just had to analyze them for preconditions and then apply their rewrites. So we did not need to be an expert. So in conclusion, I believe that simple rewrites can be used to automatically scale complex distributed protocols. We've extended this work to apply to BFT protocols as well, and we're currently building the automatic optimizer that knows how to take in these rewrites and automatically use them to rewrite distributed protocols. Thank you for your time.